So now we'll take up example 2. So we always have to read the whole question. So when 1.0 moles per liter of HClO3 is placed in an empty container at high temperatures, it decomposes into HCl and O2 gases. So they're both gases. Determine the equilibrium molarity of O2 given K is equal to 5.0 times 10 to the power of negative 16. Right, so this is a little bit different in this case because notice that we don't have a chemical equation given to us. So we do need to write out a chemical equation. And luckily, it's just based on the description that we have here. So we're going to start off by writing a balanced equation. And that's going to be the HClO3 gas decomposing at high temperatures to form HCl and O2. And we're asked for an equilibrium molarity. So that means we have our double arrows here. And that's going to be HCl. And that's a gas. Plus we have O2 gas. So before we continue, we need to make sure we balance this, right? So that's right. So remember that these equations, or the equilibrium, is based off of the balanced equation. So we'll probably want to do, we'll put a 2 here, a 2 over here, and a 3 here. So that's 6 O's, 6 O's, 2 H's, 2 H's, 2 Cl's. So now it's nice and balanced. All right. So there's our balanced equation. And then right from here, we can go into our ice table. Like we normally do. We're going to have a molarity over here. And this is nice. They gave us the molarity right off the bat, 1 mole per liter of the HClO3. So we'll put 1.00. And we're starting off with none of this. So 0 and 0. And so we'll go to put in our changes. So we have minus 2x over here since the reactant's being used up. And the product's being produced, so plus 2x. And over here we have plus 3x. So everything looks the same so far. We're going to do our 1.00 minus 2x for our equilibrium concentration of HClO3, and then our 2x over here, and our 3x over there. And so now what we're going to do is, we're also going to note that we have our K value given to us. So K value given to us is K is equal to 5.0 times 10 to the power of negative 16. It looks pretty small, but we'll see what that means in a bit. So our third step, let's go create our equilibrium expression. KEQ, or just K, is equal to the concentration of HCl to the power of 2 times the concentration of O2 to the power of 3 over the concentration of HClO3 to the power of 2. And now we can go plug all our values in, because we want to solve for x in order to plug x into those parts of the equation to get the final equilibrium concentrations. So we have 5.0 times 10 to the power of negative 16 is equal to 2x squared times 3x cubed. Make sure you put the correct value here into the correct concentration, because they have different exponents in this case, over 1.00 minus 2x, and that's squared. So this right now would look like a bit of a mess to try to solve for. So what I'm going to do is I'm going to try to do the assumption. I'm going to see if I can justify a small k approximation. So I'm going to take a little side step over here, and I'll do the initial concentration of HClO3 divided by the K value, which was 5.0 times 10 to the power of negative 16. I'll plug that into my calculator. I'll get, so initial concentration was 1 divided by 5.0 times 10 to the power of negative 16. So I'm just going to write that as 1 over 5.0 times 10 to the power of negative 16. And we get about 2 times 10 to the power of 15. So we get a very, very high K value. This is much larger than 100. So what does that mean about our assumption? Yeah, we can neglect the minus 2x at the bottom there. So therefore, assumption is justified. So we can remove this piece over here. And that's going to make our lives very easy, right? So let's go ahead and rewrite that with our assumption in place now. So now we have 5.0 times 10 to the power of negative 16 is equal to 2x squared times 3x cubed over 1.00 squared, which is just 1, right? So I'll continue here. I'll get 5.0 times 10 to the power of negative 16 is equal to, okay, so this is 4x squared. This is 27x cubed, and that was simply 1. So divided by 1, I can just leave it out. So this is divided by 1, but I could leave the 1 out now at this point. So essentially, I got rid of this because you can only get rid of stuff that you're subtracting or adding in your simplification. And then I went to evaluate all the different parts so far that I could. This just became 1 squared, so I don't really need it in there anymore. It's just the top number divided by 1. I'll clean up a little bit more, so I'll do 5.0 times 10 to the power of negative 16 is equal to, so you just have to be careful when you're doing your math. You can use a calculator if you need to, if you feel comfortable. So 4 times 27 gives you 108. And then what's x squared times x cubed? What would that be? Let's remember our exponent rules are multiplying, right? Because, yeah, you add the exponents up here, so 2 and 3. So 108x to the power of 5 there. Now we can divide both sides by 108. So cancel out that there. And so we get x to the power of 5 is equal to 5.0 times 10 to the negative 16 over 108. How do I get just x?
Say take the 5th root of it.
Yeah, so let's take the 5th root of it. So we'll do 5th root here and here. And we'll get that x is equal to, so let's go figure this out. So 5 times 10 to the power of negative 16 divided by 108. We'll take the 5th root of that, and we'll get about 0.00034127 molar. That's essentially our concentration. And now all we really need to do is go and plug it into our different concentrations that we have over here. And that's going to be our final concentration. So just before I do that, though, again, this is our x value that we found. So that was essentially our step 4. And our step 4, the main difference is we had a little side step where we had to take a look if we could make our assumption. Now we can go and find what the final concentrations are. So the concentration of HClO3, I know we said that's equal to the 1.00 minus 2x. But remember, we made the assumption that the 2x was negligible, so that should be that should mean that our equilibrium concentration is roughly equal to our initial one, which is 1.00. If we round to our 2 sig figs, we should get around 1.0. Over here, we'll do the concentration of the HCl, which was, let me just double check, 2x. And so when we do that, we get, so times 2, about 0.000682557 molar, or if you were doing 2 sig figs, 0.00068 molar. And then for our concentration of the O2, that was 3x, which is 0.00102386 molar, or to 2 sig figs, that's about 0.0010 molar. So we have our concentration of the O2, our concentration of the HCl, and our concentration of the HClO3, all determined at equilibrium. We can check our work by plugging these into our equilibrium expression to see if we get the same K value that we had at the beginning. So let's go do that just in case we made a mistake. It's a possibility, who knows? So we'll do an extra step, step 6. Let's check the work. We know that K is equal to the concentration of the HCl squared times O2 at equilibrium cubed over HCl O3 squared. And we can go ahead and plug in our values that we got. I usually put the unrounded values. So for HCl, it was 0.00068, so on and so forth, squared, times the oxygen, which was 0.00102, et cetera, cubed over the HClO3, which is 1.00, that was squared as well. That doesn't really make a big difference just because it's just a 1 there. So let's go and see if we got the right answer. So we'll cube the oxygen times 0.068 2557 squared. And I get about 4.9999 times 10 to the power of negative 16. Is that our K value that we had in the question? Right, it is. Like if you look, our K value was 5.0 times 10 to the power of negative 16. This is pretty close. It's just probably some rounding that I didn't include all the decimals, but very, very close. So that means that we were on the right track with what we did. So our justification was, our assumption was justified using the 100 rule test. So let's call this 100 rule test. And because our justification was, our assumption was justified, we were able to continue the problem without having to use any complex solving strategies for X. So just to summarize, we had a question where we weren't given an equation, so we had to write an equation out. We then had to design an ICE table for that equation because we are told that it's an equilibrium system. And so we did that, got these equilibrium expressions here for that. And then from the equilibrium expressions, we made a K expression. We plugged in all our equilibrium data and K values there. And we noticed this would be pretty difficult to solve for X in this situation. So we decided to test our 100 rule. And then once we tested our 100 rule, we saw that we could actually make an assumption since the initial concentration over the K is much greater than 100. So we could remove that 2x from the denominator there. It's basically like it's negligible. So it's almost like just having 1 squared at the bottom, which means that's gone. We then went to clean things up. So I multiplied everything here, carried the exponents in, and then we just solved for x by doing the fifth root of both sides to find x. And then we went to put that x into the concentration expressions we wrote earlier. If you did this concentration expression here, you'd see that it's pretty close to 1 anyways. I mean, we can just try it out to check, but if we did, so 0.000341278 times 2, and then you did 1 minus that, you get 0.99931, which you round up to 1 anyways, right? So it's such a small change that is considered negligible compared to the initial concentration that was there, which is why we can just go with the initial concentration value instead of having to plug all that in, since we did our assumption. So since we made the assumption, the initial concentration is going to be roughly equal to the equilibrium concentration. And so that was a full example of using the 100 rule to justify our assumption. You can go back to other questions that we did from previous lessons, and you can try seeing if the assumption will work in order to see that you get very, very similar answers. So if you go to the lesson yesterday where we did the quadratic formula, you can try this assumption again and see if you get the same answers. And you should, because it does illustrate that it's such a small difference that you shouldn't see much of a difference overall, especially when you're done your rounding to the number of sig figs as you see in the question there.